Delightful introduction. Okay, so I'm chairing the first session. The organisers are Karen Bauer, Anna Garcia, Elsa, Sibylla Schroll, and Untitled Chapter. And so, as you all know, cluster algebras were introduced in 2001 by V&eacute. And they were interested in studying the canonical basis and total positivity, though they were their main motivations. But it was soon noticed after that that cluster algebras could be codified, and this has led to many new ideas in representation theory. So examples are higher homological algebra, Calabi-Yau categories, and tau tilting theory. On the introduction to the conference. So the aim of the conference will be to share the latest developments in areas and to look at future development. So some illustrative points to make. The meeting is being recorded in live stream. So if you don't want to be recorded, you need to keep the microphone and camera up. I guess you need a mask if you're here. And use the chat button for any questions. That's really aimed at the online participants. The live transcript will be active if you're online, and participants can turn this off by clicking on the live transcript button on the bottom of the Zoom screen. Okay. And Matt Pressland is here. Matthew Pressland, he's the moderator. Okay, so I'm sure after the workshop last week, you all know everything you need to know about cluster algebras, so you're ready for the new developments. And today we've got 4 speakers: Ralf Schiffler, Ralf Schiffler, Karen Jacobsen, Gergi Klammerno, and Thomas Gruser. So without further ado, I present Ralf.
Thank you very much. I would like to thank the organizers of this workshop for listening. I will talk on the board, but I mean, I will write on the board, but I wanted to show 2 pictures before I start. This is number 1. So it's a picture of Sergei Fomin and Andrei Levinsky and Isaac Newton. And if you compare these 2 paintings, I mean, this picture was taken here at a workshop at the Newton Institute in 2001. For the people who are on Zoom, you cannot see right next to me is the original painting that's there in the background. And so this was, as Bethany just said, it was 20 years ago. This was when the cluster algebra started. Yeah, so here we are 20 years later and still talking about new developments. My second picture is also local. This is the gates of the building right next to us. So if you go out, maybe 50 meters, not even that you see these 2 gates. And I'm not sure if you can see it, but there are 2 knots in wrought iron there in these gates. On the left, you have, oh, I don't need to say their names maybe, but these are the smallest non-trivial knots, which trivial Alexander polynomial. And I was happy to see that because I'm going to talk about knots and Alexander polynomial. So start. Going to work with ronique Bazier-Matte, who is a postdoc at UConn. So I'm talking about the connection between knot theory and cluster algebras. So our goal is to associate to every knot a cluster algebra, and then in a meaningful way. So first, let me show you how this goes. I'll take a knot. Let me try that again. I practiced this many times. Now I did it in a different way. This is actually the figure 8 knot. It's a very small, very simple knot. I will use the letter K for knot diagram. So knot diagram means the thing I have drawn there. It's a projection in the plane. Sometimes I want to consider it as a graph, so I will use the notation K0 for the crossing points. K1 for the segment. Actually, the segments, it's convenient to label them in order as they appear along the knot. So if you choose an orientation here of the strand and start somewhere with labeling a segment 1, then you can just continue 2, 3, 4, 5, 6, 7, 8. Following along the knot. Oh, by the way, I was told that sometimes when you're on Zoom, it's hard to see what is written on the blackboard. So there's notes which are either in the chat or there's a link in the chat to the notes, which might be easier to see. Okay, so there's these 8 segments here that I labeled 1 to 8, and then I also want K2, which are the regions given by the diagram, including the unbounded region on the outside. Well, we want to get a cluster algebra, so we will associate a quiver to this. Okay, the vertices of the quiver are exactly the segments of the knot. So let me write the numbers roughly the same way as they are there.
Recording.
Okay, so these are the vertices, and then we have arrows, and well, let me just say we're going clockwise around the crossing points. Okay, what does that mean? So there's a crossing point here, and it has 4 segments attached to it. So there are 4 vertices related to it. I go clockwise around. So I go from 1 to 4, then to 8, and then to 3, and back to 1. Second crossing point is 4, 7, 5, 8, and up to 4. Then I have 2 more, 1 to 6, 2, 7, 1, and 2 to 6, 6 to 3, and 3 to 5, and 5 to 2. And so revert. You see, there are 2 types of cycles. Each crossing point gives you a 4 cycle. And then each region in the knot also gives you a cycle. So I will define a potential as the cycles from the crossing points, or I would just say K0 cycles, and then subtract from that the region cycles, so K2 cycles. So this is very similar to a diagonal algebra, except I don't say this. I don't require this to lie on the torus. And then, well, there we go. We have a quiver with potential, so now we can take the cluster algebra. And also the Jacobian algebra of the potential. And well, voila, we have associated a cluster algebra to a knot. But of course, the question is this in any way meaningful? So the goal here is to find information about the knot inside the cluster algebra. So what we are going to do is we will construct cluster variables which will specialize in the Alexander polynomial of the knot.
Ralf, we have a question in the chat.
Yes.
Alexander Shapiro. So there seems to be no difference between the over and under crosses.
Yeah, very good question. Yes. So already you see, you lose a lot of information here, because if I would change this to this, you would get the same quiver, same cluster algebra. The quiver doesn't take care, doesn't see if your strand goes above or below. So the cluster algebra itself cannot be an invariant of the. Okay, so I want to construct cluster variables, and I will do so by constructing modules over this algebra. Well, like this, for every segment, actually, I construct a different module. An indecomposable E module, and well, I'll denote it by T of I. I'll do so. I'll construct this module as a quiver representation, and so I need to define vertices. I need to define vector spaces on every vertex. And I need to define linear maps. I will just do the first. So the first step here is to partition a set of vertices. The vertices of the quiver, I remember this is the segment of the knot, and I will addition the set of all segments. The first at d equals 0 is very easy to say. This is the set of the segment I and all segments at ci. This mean I will show you in the example. Yeah, so let's draw this picture again. Yes, I ignore the over-under crossing here in this picture, but so I take here example I is equal to 1, and then I want to color this ki 0. So the segment 1 is this one here, so this one will be in my set. Then every segment that sees this segment 1, so by seeing, I mean they are at the same region. One region, and then we have the outer region. So this is K0. And let's go back to the general case. This is always K1I0. This is the right definition. And Ki1 is well, the boundary of k minus ki0. This is sometimes all of it, but in general there's more. It's a little bit technical, so I will not tell you how to do that precisely. In our case, after the first step, we are done. Ki1 is all the rest that you don't see yet. So these three segments, which were 2, 5, and 8, who is this one? And then we continue. So K2 boundary of K minus Ki0, Ki1. And also plus something else. Keep on going until you have completed the partition of the whole set. And then, well, D is the dimension of the vector space at the vertex. Dimension. Our representation Ti is D at every vertex. Okay, this is the first part of the construction. The second part would be to construct, define the linear maps. And this is a little technical, so I don't do this here. In the example, these maps are actually determined simply by the dimension vector because it's so small. In this case, just support at 2, 5, and 8, and then you see here there's the representation has identity matrices on these two arrows. And usually we denote this just by 5, 8 like this. And that's the module we associate to this segment. And now I give you a little exercise to show that if you do the same for I equal to 2, then you get 8, 3, 1, 4. And here, what you should notice is these two modules are very different. Right? They don't have the same dimension for one. They have very different module structures. This one has a simple socle. This one has two simples in the socle. And well, you could say they're actually quite similar still. They're both of type A and small, but this is only a coincidence because this is such a small example. So in big examples, the modules that you get are very different. Okay. Okay, so part 2 is about knot invariance. Well, a nice title, but I just talk about one of them. And so a large part of knot theory is to find invariance, algebraic invariance, usually to be able to distinguish two knots. And one of the really classical ones is the Alexander theorem. delta is a polynomial in one variable. And this is actually defined only up to a power of t. Alexander did this in 1923. And so, for example, the figure 8 knot the polynomial 1 minus 3t plus. And well, this is an interesting invariant. It gives you information about the geometry of the knot. It has geometric definitions, algebraic definitions, and combinatorial definitions. And sorry, I won't give you any of them. Instead, I want to tell you about one construction by Kaufman. Which is using Kaufman states. So was done in 1983. Yeah, he realized Alexander polynomial as a summation over what he calls states. And then, well, there's a sign, and there's some weight function. That's Kaufman's result. And actually the states form a poset, and I have drawn this poset here for the figure 8 knot. Here, all this is also relative to a segment. So I'm still having here the segment 1. Remember, this is this piece. So the two regions next to the segment 1, they don't receive a marker. But then you see here 4 red dots, and how do I distribute them? Well, every crossing point has to have a dot, and every region has to receive a dot except for these two. This is one possibility. I have a red dot for every crossing point, and there's no 2 points in the same region. That's a Kaufman state. And then for this particular knot, there are 5 of them. They're all here. And then there's a certain order on these states. So there's a way to say what's the minimum state, what's the maximum state. And there's an operation which takes you from here to here. If you look at it, I know it's confusing with these dots there, but if you look what is different in these two pictures, then you see that, well, these 2 dots here have changed position. And so why can you do that? Well, here's a segment which has 2 dots. Whenever you have that, you can move the dots across the segment. Get this configuration. And if you remember, the segment here in question was labeled 8 up there. This is why I record this here as 8. Because this was 0 state, and this is the state which has used the operation 8. Similarly, the other, so the poset has the shape that's indicated there on the right. And yeah, so you get this picture. And
how do you count that there are 5 different but there are 5 different situations like that and not more?
Exactly 5 in this case.
But, is there a way to
by hard work
compute it?
Yes, yes, there is. So there's a way to construct the bottom state by peeling off the outer layers of the knot one by one, like peeling an onion, and then consecutively putting the markers at the right position. And then you construct everything by these elementary moves. Go up in the poster. This unique minimal state and unique maximum state.
Like a perfect matching thing.
Yes, exactly like a perfect matching. Okay, so part 3 is results. So for all segments, first of all, the Kaufman state poset is isomorphic to the state of poset of submodules of Ti. Right, so for every segment I, we construct this module Ti. They all look very different, as you remember, but they all have the same poset as the Kaufman state. The Kaufman states also depend on the segment I, of course. Part B. So maybe I said this not in a good way. So these two modules have different posets. The posets are not the same. If you change the segment, then the Kaufman states also don't give you a different poset. Whatever segment you choose, the Kaufman poset and the submodule poset, they are the same. And then part B. Well, maybe I should say first that if you look at the quiver-Grassmannian of this module Ti and compute its Euler characteristic, then it's always 0 or 1. It's very very unusual for a complicated module, but that's the case. So then the F polynomial has a very, very simple form. The F polynomial of Ti, well, it's just the sum over all submodules. I don't have to write the Euler characteristic because it's just 0 or 1. This vector y raised the dimension. So this F polynomial specializes the Alexander polynomial. And yeah, I run out of space there, so maybe I just continue here. Okay, so when setting three possibilities, your variable yj can be negative t. This happens when the segment j goes from an undercrossing to an overcrossing. This difference in the over and undercrossing comes here in the specialization of the F polynomial. If it does the opposite, then get T inverse. And well, if it doesn't change over or under, it just remains on the same side, and it's just a negative one. A time up, or did we start late?
Couple of minutes, I think.
Okay. So then let's look at these two F polynomials here. So let's take T1. The F polynomial, you can see from the representation, since this knot is alternating, the specialization is actually very easy. The even terms become negative t, and the odd terms become negative t inverse. So this whole thing specializes to 1 minus t plus t squared minus t. It's the same as I said earlier. Yes, this works. This is the Alexander polynomial. And well, we can do this for T2. I'm running out of time. So that's our theorem for now. Our work in progress or conjecture is that if you take all these TIs for every segment of the knot, then you actually get a cluster in the cluster algebra, and whose quiver is opposite to the quiver of the knot. And then you can think about the correspondence sending the original cluster to the cluster that you get from the knot. This is a cluster automorphism, and it seems to be of order 2. Okay, so this is all the time I have. Thank you very much.
Thank you, Ralf. Are there any questions? What happens if you apply Rademacher move?
Everything changes. Oh, okay. It depends which move. If you do a Rademacher 2, the rank of the quiver changes. You have 2 more crossings. So the cluster algebra changes. Everything changes. Except the Alexander polynomial. But yeah.
Sorry, I think you just didn't finish your sentence. And the theorem was that if you make this substitution, then you get the Alexander polynomial.
Yes.
For every I.
For every I.
Okay.
All these modules that you define, each of them gives you the Alexander polynomial. And they all together form a cluster. Let's conjecture the last one.
So is there any role for matrix mutation? I mean, can you mutate a knot?
A single mutation doesn't make sense really in the knot, but certain sequences can interpret as certain moves on the knot. It's not necessarily the same knot that you get afterwards. So we have certain sequences of mutations which will make a Rademacher 3 move, but up to passing the strand through another strand. You can have some interpretation of certain mutation sequences. A single mutation, I don't know how to interpret it. I mean, mutations of this quiver usually do not preserve the structure of it. That you have 4 cycles, everything is an oriented cycle, and then every 4 cycle gives you a crossing.
We have another question over here.
No. Is the Jacobian algebra finite dimensional?
No. Well, in this example, yes, but in general, no. That's one of our biggest problems.
But for example, Rademacher, well, this young Baxter move. So can you represent it as a sequence of mutations?
What we can do is something like actually, I think it looks like this. So it's not Rademacher. Speaking, there's the problem with the over and under crossing. So I have to think. I think it goes then behind here and over here.
And
usually, you would have both crossings here behind, and here you would have both crossings in front.
Okay.
This we cannot describe. So this is not a This is a different knot on this side. This move corresponds to a sequence of mutations.
And what about variable mutations? Does it have any meaning?
I don't know. I mean, the F polynomial does, and the G vector should also have something to say. Maybe you have to specialize it as well, but I don't know yet.
I have a rather tangential question with respect to this algebra that you defined. So you can define the quiver associated to the knot, and then you could define other relations, right? One of them could be thinking about the knot as a Brouwer graph somehow, and having the Brouwer graph algebra, right?
Maybe.
But so in this case, the relations could go as like the difference of cycles of two vertices that, of the cycles that are going around one crossing point. And do you think that your modules would be also modules over this algebra? Maybe we need to do some examples.
I don't know. I think these, I mean, the example I gave is very simple, very deceptively. So the modules in general look not nice. But
right. Yeah.
Seem to be very specific to this kind of relation that we have here. But yeah, I don't know much about the Brouwer graph algebra, so I'm happy to check.
Okay, thank you.
Okay, great. We should. Another question.
Well, I was going to clarify. It's Daniel Labadini asked him just to clarify the relations, based on what Daniel was asking in the chat. So in your example, the cycle 1,6 to 3,6,1,6, around the outside, that's also in W, right?
Yes, that's one of these. It's a relation coming from the outside region.
Yeah. So one of the consequences is that all of your relations are commutativity, and there are no zero relations. Right?
That's right.
Okay. So so you can make it finite dimensional by completing. It just is infinite dimensional, and that's the way
it is finite dimensional. The completed one in this example is, but in general, it's not.
Well, I think it's still, if there are no zero relations, it must be infinite dimensional.
We have to complete.
Even if you complete, there's no zero relations.
Well, but still, it's finite dimensional because you get a path that's equal to a path that is much longer but contains the original one.
Ah, yes. Sorry, it's the sphere. It's the sphere.
Similar to algebras from surface triangulations, they're also finite dimensional, although there's no zero.
Yeah, sorry, I forgot the sphere was so bad. Yes.
Okay, great. So this is causing lots of interesting questions. Thank you very much, everyone. We will continue with Karin Jakobsen's talk in 5 minutes at 1:45.